welcome. So, in this lecture we are going to talk about overview of digital pulse width modulator architecture. So, first we will talk about digital pulse width modulation, the requirement and the challenges, then the counter based DPWM architecture, other DPWM architecture which will include delay line DPWM as well as hybrid DPWM architecture. So, first we want to talk about digital pulse width modulator. So, here we will summarize the three different architecture, but first we will go over the basic counter based DPWM. How does it work? So, if you take a DC-DC buck converter for example, and we are talking about voltage mode control, and we already know that ADC, and then from this block onward we have everything in digital. Okay, these are all in digital. Now, here this is the compensator and this is the controller output. So, this controller output is actually stored in a register, and then output of the register, that is the same thing, but we need to synchronize with some clock, and this actually this value is compared with the sawtooth. Now, this question is how do you generate this sawtooth? That means we have to generate this kind of sawtooth waveform like this. How to generate? So, the easiest way, you just take a counter and you increment, that means you counter 0, 1, 2, 3, and if it is a modular counter, that means a 2-bit modular, that means it will count 2 minus 1, that means counting, that means NR means if it is if you want to count from 0 to 13, then it is a 14 modular counter, that means 14 minus 1. So, it will upper limit will be from 0 to 14 minus 1. So, that means for NR it will be 0 to NR minus 1, and it will again reset and it will repeat. So, this is a periodic signal which will actually hit the upper limit and NR minus 1, then will reset to 0, and that is called modular counter, and you can get detail in this book. So, in this architecture, if you take this register output which is here, and if you compare it with this sawtooth, now we want to make sure, that means when you talk in our HDL coding about Q format, so each of these have a finite resolution, that means DPWM will have a finite resolution, as well as this number which is stored in the register, it will also have a resolution. So, whether both are 8-bit number, what is the bit size, then how do you decide the resolution? So, that we will discuss when you go for fixed point implementation. But you remember that this value of VH, this can change in the increment of this, it cannot take any in between value. But if the resolution of VH is higher than this DPWM, then you can also get in between value. So, that means how are you setting? So, it is recommended that resolution of VH should be same as the recommended the resolution of this staircase, so that you can map to any of this number. So, they will be equal. That is why when they are equal, then you are actually shifting the register, that means you are storing in the new value. So, you are updating. Now, the question is, if you go for this counter, I mean we want to generate a switching period of TS, and in order to get TS, so how many times this you have to count? That means if you are talking about n bit this DPWM, then we need to count from 2 to the power n, that means 0, 1, 2, 3. So, if it is n bit, let us say 3-bit DPWM, 3-bit DPWM, then it will come from count from 0 to 2 to the power 3 minus 1, that means nothing but 7. So, it will from 0, 1, 2, 3, 4, 5, 6, 7, again it will repeat from 0. So, that means it will take total 8 clock cycle, and that clock cycle is measured with respect to this time period T clock. Okay. So, for 3-bit resolution with a time period of T, your clock frequency will be 2 to the power 3 into switching frequency. Now, if you imagine, if you need a switching frequency of let us say 10 megahertz for example, and you need n DPWM resolution to be 10 bit, then what is the clock frequency requirement? It will be 2 to the power 10 into 10 megahertz. So, it will be almost 10 gigahertz, because 2 to the power 10 is 1000, I think 1052, right? It is 256 into 4, it will be 1024. So, it is almost 10 gigahertz clock, and which is practically impossible. That means the requirement is that you need to meet a minimum resolution, because the resolution of this DPWM will define the resolution of the duty ratio. Resolution of the duty ratio. Because if your duty ratio resolution is poor, then there are two problems. First of all, you will not be able to meet the voltage regulation requirement. That means the duty ratio resolution DN will be, what is the resolution? That means what resolution can you achieve? It will be the time period of the digital clock divided by the time period of the switching clock. Okay. So, if you take 100 times faster clock, then it will be 1 by 100 is the resolution. If you take 1000 times, so accordingly it will be selected. Now, imagine if your output voltage V0 nominal value is 1 volt, and you want the voltage regulation point, that means V0 can be 1 volt and plus minus maybe less than 1% of this, less than 1%. That means that voltage regulation should be less than equal to 1%. That means what is the resolution? 1% means it will be 10 millivolt is the resolution. So, in order to get 10 millivolts, so you need a resolution minimum of 1 by 100, and if you get a better resolution, you need more. So, that means in order to meet the required resolution, the duty ratio resolution need to be higher, and if the duty ratio resolution increases, then your f clock frequency requirement, which is 2 to the power n time FSW, that increases. So, that will become impractically high, and you may not be able to implement. So, that is the bottom line of this counter based architecture. That means you need 2 to the power n time higher clock, digital clock, for a high frequency switching converter to generate this n bit resolution, 2 to the power, that means n bit DPWM. So, this is, this will put a limit for high frequency application. Then what is the alternative way? So, that means this is a counter based DPWM. Now, that means if we eliminate, so we know about all this requirement. So, the challenges we have discussed, challenges means the clock frequency requirement is too high for high frequency plus high duty ratio resolution application. And that will put a limit. Then what is the alternative way? It is called delay line approach, where again this part is common, that resistor is there and this has to be compared. Now, we need to compare this value with the sawtooth waveform. So, here we are not using any high frequency switching clock, we are simply using the switching frequency clock itself, but we are using many buffer circuit. These are the buffer circuit, and each buffer circuit will have propagation delay. And what is the buffer circuit? We know the buffer circuit is nothing but two back to back inverter. That means each buffer circuit will require 2 plus 2 4 transistor, and each of this inverter will have the propagation delay. So, the buffer circuit will have a propagation delay. How does it work? So, if this is 2 and you say this is a 2 to the power n mux input, that means an input number of input are 2 to the power n and single output. If this number is n, then 2, it will take this M2, because if you take, we talk about mux, right, this mux. So, let us say it is 0, 1, 2 dot 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 dot. So, these are the channel I0, I1. So, in this case it is M. So, let it be consistent. That means here we are talking about M0, M1, M2 dot dot dot, and the output is output is here, let us say Y. So, it is Y. So, now if we want to map That means if the select line say that select line is that here, what is the select line? Here is a VHN. If this equal to 2, this channel will be selected. So, we are talking about this particular channel, and this channel means if you take the original switching clock, it will be delayed by 3 buffer. That means if you draw, this is the original switching clock, which is the switching clock. The first delay, because this delay, due to this delay, this will be delayed. Then the second stage delay will have another delay compared to the first stage, and the third stage delay will be another delay. And since the third stage output is going, so this will reset, this high edge will reset this pulse, and the clock of this FSW will set the pulse because it is a trailing edge modulation, and this will reset. So, this will be your duty ratio. That means the resolution of the duty ratio will be in the order of the resolution, the difference between the buffer delay. Okay, that means if you can get more number of mux input line, and by decreasing the delay, you can get a finer resolution. But the problem is this delay is decided by the process technology and the supply voltage VDD. So, you cannot assume all buffer circuit will have identical delay, because there can be some delta variation, and that variation can cause a linearity issue in this case. So, here the resolution will not be linear because all delay may not be identical, there can be some variation. So, that is one of the problem in this architecture, and this architecture was proposed in 1991 from MIT. Then the next architecture, that means that is the disadvantage that we discussed. The length of delay line is too large if you go for high resolution DPWM, and then the linearity is, and that can exponentially increase as the number of DPWM resolution increases. And secondly, the linearity is a problem because all delays are not identical. Then what is the solution? Again, from the same group, it turned out to be another architecture which is hybrid. That means you can use two structure. One is the delay line, which will reduce the clock frequency requirement, but it will give a fine tuned resolution. But the coarse resolution can be achieved by the counter, because suppose if you use, let us say we need 8-bit DPWM. So, what we can do, we can use, let us say 3-bit counter base. That means that means the clock frequency requirement will be 2 to the power 3 times FSW, and we are using remaining 5-bit will be my delay line. Then how many number of mux input will be needed? It will be 2 to the power 5 minus 1, or here it will be 2 to the power 5. Yeah, it is almost buffer. How many buffer or delay line? So, delay line, for 5-bit delay line you need 1 minute, same number of, almost same number of channel. So, number of delays, or basically these are the buffers. Okay. So, by that way you can reduce or you can improve the linearity issue, because you are not using too many number of delay line. At the same time, you can get counter base is very good in terms of linearity, but it has a drawback of the clock frequency requirement. So, you can optimize. So, you can see here in this architecture, if you take the MSB of this to use in the counter base, and the LSB actually gives you higher resolution. MSB is the coarser action. So, then LSB will go to the select line input, and accordingly the signal will be delayed. So, how does it work? That means, let us say if you take this LSB to be 2. So, it will take this line, that means M0, M1, M2, this will be the line, and this modulo counter is a, suppose we are talking about 8-bit DPWM, and this is, let us say 3-bit, and this is a 5-bit. Okay. So, then if LS equal to 2, it will select this M0 line, and it is already a DPWM, and this DPWM resolution may not be very high, because we are using a coarser action. But once this is enabled, you see this pulse is enabled, that means when it will cross this part, and this is the 1, and so this is the line when it will intersect, then the first M0 there will be a delay. So, this delay will introduce this delay, then it will go to the next stage. By that way, here will be my 2. So, this will be my input that we are considering, and your duty ratio will be like this, because at the beginning of the clock the switch will turn on because it is trailing edge, and once this select line is decided, when this select line is going high, that edge will reset this pulse and it will switch off. So, by that way we can actually realize this DPWM architecture. This is called high bit DPWM architecture, and here the clock frequency requirement will be 1 by, that means the ratio of the clock, T clock, or I will say F clock frequency will be 2 to the power m DPWM minus m. What is m? The m is decided by m bit, I would say this is the m bit delay line. So, that means you are effectively reducing the number of the clock frequency, this into FSW. So, you can reduce the clock frequency requirement, and by that way you can improve both linearity as well as you can also reduce the clock requirement, and this is a very popular approach for high frequency DC-DC converter DPWM architecture. So, you can get detail about this architecture in this book. So, in summary, we have discussed various digital pulse width modulation, their requirement and challenges. We have discussed counter based DPWM architecture, we have discussed delay line DPWM architecture, we have also discussed the high bit DPWM architecture and how does it work. So, with this I think we will get a reasonable idea about how to implement, because we will implement some of this architecture using HDL. So, with this I want to finish it here. Thank you very much.